Right, Year 12, this is again a bit of a strange chunk, but it's one of those things that people normally don't think about when they're thinking about electricity, but you need to have that awareness. So, we talked about last time in section 2 about trying to find out about components. You plug something into a circuit, you want to know what's going on. So here we have our current, for example, flowing in, our conventional current flowing from our plus end to our minus. And how much flows through that depends obviously on how much you turn up the battery, how much energy you supply to the charges. However, we want to know what's going on at this point. So what we want to do is, and the hard bit about electricity is we can't see what's going on, so we need to use meters to measure it. And there's basically one designer meter, two maybe. And what they do is they will measure the same thing. They have some resistance, and as resistance flows, as current flows through that, then what will happen is it will cause a reading to be taken. Okay, usually a potential difference it'll measure. So actually all meters in a way are voltmeters. But, and this is the key bit, what we do to the resistance inside, we make them work in different ways. So we're going to use basically galvanometers, which are the basic meter, but named after Galvi, who did the original work on electricity. But they're magnetic meters, the ones we're going to use. They are analog. They have a dial, and it moves on the scale. What it does is that works on magnetism, because there's a little coil and you can see it, and that magnetic force gets bigger when you create more energy in that, so when you have bigger voltages. So again, it's measuring voltage. However, when you put different resistances attached to it, it behaves in different ways. So let's consider what we want. Here we have a current flowing through our device. What I want to do is see how much flows through that, so I'm going to put an ammeter in. But the crucial bit is, when I put that ammeter in, I do not want that to change that value. If that has a bit of resistance, then I've increased the resistance in my circuit, and so that was going to usually get smaller, depending if you change the voltage around from the supply. So as long as you keep the EMF the same, you basically get the same, a smaller current if you put an ammeter in. Ideally, they would have no resistance at all. Okay, so ideally that is true. Never quite, it's usually 1 or 2 ohms. So if you have something that has a very small resistance here, we need to connect this in a different way. But the vast majority of the time, what we do is we'll connect it in series, because you want to see how much is flowing through that. So you will connect your ammeter so the same current will flow through the meter as the device. Now, our voltage is our energy given out. Okay, so it's to do with that loss of energy to the surroundings. And from our equation, that is the voltage times by the charge. Okay, so voltage is energy from each charge that's given. So we want to find out, to make this work, we need to find out how much energy it's got here and how much energy it's got afterwards. Then you have that difference in potential energy. Okay, so what we need is, we will need to measure energy before and afterwards. We will connect our meter to measure PD across. Again, crucially, we don't want to affect anything in terms of the readings. So if this has a small resistance, like this one, then what will happen is that some current will still keep flowing through here, but suddenly you've got an additional path for the current to flow, so a lot more current will flow around. So we'll get a little bit of current still flowing through this, depending what its resistance is and how it opposes current, and a lot going around, bypassing it. So to not affect this result, which of course would affect this as well, because this reading would go right up, we want to have a really large resistance. So again, ideally, we will have an infinite resistance. Okay, those are your ideal meters. In reality, it's probably nearer hundreds of thousands of ohms, so hundreds of kilo ohms. If you use a multimeter, they're a bit better, maybe 2 or 3 mega ohms, maybe 5 mega ohms. So pretty big, but again, if this is mega ohms of resistance, and that's mega ohms of resistance, then the current is probably going to be about the same, so it will affect it. So what you can do, if this, for example, is a really low resistance, and that's not quite low, then you can connect the voltmeter across it, you can do different things. Okay, but the ideal is infinite resistance, so no electricity escapes around, no charges flow that way, and this has no opposition to current, so it doesn't prevent that current flowing, doesn't reduce that current in any way. Now the best way of doing it, as I say, is have the ideal things, but they don't exist. But we do have something that is very similar, and that is a rather complicated looking resistance meter or potential difference meter known as the oscilloscope, or the cathode ray oscilloscope. So CRO is what we tend to call these, and this effectively is just a voltmeter. And so our main scale is labelled up as volts for division. Okay, that will be the Y gain. What it is, if I bring a diagram in, is a graph. So all it is as a dot goes across with time, and we can adjust how quickly it goes across with something called the time base, we can actually see how the voltage changes, the potential difference changes with this. Now, I've asked you to do some research on this, and if you don't need to go much into what's inside the CRO to work out that actually the thing that makes our dot move up and down on our y-axis, our y gain, our multiplying scale, is actually caused by a gap in a circuit. And a gap in a circuit has infinite resistance. So the resistance of these, the ones that have been used for the last 40 years anyway, the resistance on these is infinite. So this is perfect. This will give you the truest value for potential difference in a circuit. Okay, so even if we're not using it for anything fancy, it will always give you a better reading. Now, most of the time we're going to want it to see how things change over time, and we've already seen it for waves, for example. You're looking at the measurement from the voltage. If you have a device, a component like a microphone, then that's actually that's creating a potential difference when you speak into the microphone. And so you are measuring the voltage output from that. So our sound wave is transferred into an electrical wave, and maybe it looks like this, and it's alternating. And what it does is electricity flows one way, then it flows the other. So 0 is always in the middle. Okay, so this is an AC signal, an alternating current. If it's not swapping direction, then it's known as a DC current, direct current. It has one direction, but just be wary, it can still change. Okay, sorry, that's a DC voltage, I should say. DC, a little bit dodgy phrasing because it's direct current, but we tend to call everything DC or AC, even if it's not current. But yeah, that's just an unsmoothed DC current or voltage. Okay, and I say DC current or voltage because the voltage will have come from the current flowing through a resistance, so they're equivalent, they're scaled up. V is always proportional to I, as Ohms said, Georges Simon said. So if we do have something that is smoothed, okay, not like our power packs but like our battery, for example, then the voltage will be fixed at a certain value, and you'll just get a nice horizontal line. It won't vary over time. The value here on your graph obviously depends on the scale that you've chosen to put this as. So on our oscilloscope we have one control, the Y gain, the volt per division, that gives you the vertical scale, and you've got another one called the time base that gives you how far apart these are in time. Is it a millisecond? Is it a second? Is it a microsecond? So you can change the scale vertically, change the scale horizontally. And those are your two main components. All the oscilloscopes we have are dual beam, so you'll have two lots of traces, so you could have two lines going on at the same time, but they're both adjusted in the same way. Okay. The interesting thing is you don't have to have the same scale for two lines. There we go. So really powerful device. So find out how it works, find out what's going on, find out about the Y plates and the X plates, which is moving the dot in the Y direction and the X direction, how they do it. Make sure you're happy with the Y gain. A lot of you have already done the measuring the frequency of a sound from my video. Great. That's all you're doing. All you are doing is reading the time or voltage scale on a graph. Okay, so simple in terms of what it's doing, but it's the only way of getting the correct potential difference. You do need to know your way around this, but the only other thing that is worth looking up and you need to find out about is alternating current. It's worth knowing your way around. All circuits could work on DC or AC, and so because AC is changing, we tend to give it certain names. So there's your, for example, your peak voltage is the voltage at the peak, but you'll have something called an RMS, and this is actually probably about the right level for RMS, and it's equivalent to the DC. So there's certain phrases to work out. Again, there's things that make it more accurate. Oops, here we go. So we'll often measure from top to bottom because it's just more convenient, and that's known as the peak-to-peak voltage. None of it's genius, but just make sure you're happy with the kind of way around it and how to use the oscilloscope. And often, again for waves, how to measure the frequency from the oscilloscope as well. So just make sure you're happy with that one. Okay, that's it guys. How to use meters and the principles behind meters. Thank you.